So what Hill was doing, he was guessing at the shape of a lunar orbit. And the way we can think of it, he was saying, the orbit looks to me should be here, 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 some number of points. And then he put his solution into a Lagrangian solver. You can think of it in multi-shooting way, saying that if I start here and integrate exactly my position, if my solution is not exact, I'll make an error, I'll miss the next point, and you can do this for all the points. And that's what Lagrangian formalism does, in a way that you didn't understand when you took the course in classical mechanics. It globally satisfies the local equations, the tangent equations, every place. And that's a solution which is characterized by action or Lagrangian function, which has a property that its first variation is zero. So that gives us the notion of classical solution from Lagrangians. World classical because in the quantum field theory this is used all the time as a classical underpinning of quantum field theory. This has many names in engineering. You write an error function, which is not necessarily Lagrangian, but some sum of squares or something that you're trying to minimize. It's called multi-shooting in the way I explained it. It might be called collocation, making that all these points are located correctly for this to be a solution. And the solution is extremum of some function that measures deviation from the correct solution. Now, for him to solve it, he had to do what we also have to do in the classical case, basically some Newton method. If you had some errors, then it's what you want to do is you want to find in linear approximation how to improve this in the next step. You do this by computing a matrix. It's this Jacobian matrix for forward in time evolution. And it's called Hessian if you allow yourself to vary all the points around. And to be able to invert that matrix and use it to improve your calculation, you have to compute the determinant of this matrix. Now, this matrix is very large. This matrix is small in the sense there are a few degrees of freedom, and that's the size of the matrix. Doesn't matter how long the orbit is, but not in the Lagrangian formulation. A good orbit, you have to put lots of points in to make sure it's accurate. So this is arbitrarily large. And in principle, as Poincaré understood, it's actually not a matrix, it's a functional matrix. It's a set of derivatives of a function, and you have to compute this to improve your guess. So it's big. And you can't do this by hand, but what he did is he approximated it by going to Fourier space and saying, well, this is almost a circle or a nice smooth curve. Let me just use few Fourier modes. He used only 3 Fourier modes, which he could do by hand. He got himself a good lunar calculation. And here comes the amazing thing. One calculation requires the forward stability of your orbit. That's this, the Jacobian or fundamental matrix, Jacobian of the orbit. And this tells you that you move forward in time. If this has expanding eigenvalues, your errors grow and you have chaos. But here, you seem to be doing something totally different. You take a whole orbit, you forget that there is time, just use it to label points on it. You jiggle the whole orbit, and you look at second order effects of jiggling this way and that way, get this Hessian, And then you compute that orbit. So what's the relation between thinking forward in time and thinking solution has stability, the global stability, not local by little perturbations locally. So what he established is that the Hamiltonian forward in time determinant you compute here, which is determined with small matrix, equals the determinant of this huge global matrix. So this determinant is called Hill's determinant, and this formula is called Hill's formula. And usually people mean that what it means is that I'm solving some problem with long periodic orbits. I might solve it by some method like graduate student solves it when he actually computes it, because this is undoable, as I tried to explain. But to understand its stability, we think forward in time. And it's okay if you live in 19th century and you've never heard of special relativity, you've never heard of Ising models, you've never heard of quantum field theory, you've never heard of general relativity, but you've heard of any of those things, you'll realize that picking some kind of spatial configuration and evolving time is a very arbitrary thing, because what you call time and what you call space is very arbitrary. And when you actually understand it, this thing is actually uncomputable in spite of anything your nonlinear dynamics professor has told you, meaning me in a previous course or some reputable professor, that you should actually compute this infinite matrix, which seems hard, but eventually you realize, no, when you do it, that's the thing to do. It's elegant because you're not breaking space and time symmetry by some arbitrary methods. So that's what I want to explain next.